Bum, ba, bum. There's Indiana Jones, and he's being pulled out of the snake pit at some time that is 3.4 meters. Indiana Jones weighs 70 kilograms, and the rope breaks at 755 newtons. All right. Anyway, sorry. All right. Here's what we got. Indiana Jones being pulled out of the snake pit. The height of the snake pit is 3.40 meters. The tension or the time is what? The mass is 70 kilograms, and the rope will break at 755 kilograms. Do you ever kind of understand why they give you like this? The only equation I've given you in this chapter is F equals ma. I mean, technically, I did give you F equals force of friction equals mu times the normal force. But that's not really a separate equation. That's really just kind of saying this force of friction is defined as some scaling factor of the normal force. Really, the only equation I gave you was F equals ma, to be honest with you. So all of this stuff right here, relates to the acceleration.
Okay.
So if I'm pulling Indiana Jones out of the snake pit, and I just yank the thing, because I want to get him out of the snake pit as quickly as possible, right? What's going to happen? Like if I attach him to a jet, and as soon as he like I attach the rope up here to an airplane,
then it would probably break.
The rope will just snap, right? The acceleration is way too fast. Or even if I put it on a car, or I put it on a pulley. Let's say I put it on a pulley and I, just like as soon as he grabs the rope, turn it on full blast. Because obviously you want to get him out of the snake pit, right? That's no good. You don't want a snake pit.
That makes sense that the tension is related to the acceleration because tension is a force.
There we go. All right.
So
Let's add the forces in the y direction is equal to mass times acceleration in the y direction. Cool? What forces do you see in the y direction? Acting on Indiana Jones. You have the tension, right?
Yeah.
And then what else do you have?
Weight.
Minus mg is equal to ma. Now, if it's alright with you, I'm going to use these numbers to help me figure out A. And I'm going to use old school mechanics to do that. I'm going to say delta x equals v naught t plus 1/2 at squared. Is that the equation I want?
Yeah.
Sure. Alright. The v naught is 0. You didn't start off with any acceleration, or any velocity to begin with. Acceleration is what I'm trying to look for. Okay, fine. So that's delta y, or h in this case, is equal to 1/2 at squared. So I've got 2h over t squared equals a. We cool?
Yeah.
Alright. So I'm going to rewrite this thing, but instead of writing an a, I'm going to write 2h over t squared. So I have t equals mg plus m times 2h over t squared.
That makes sense.
Okay. T is equal to m times gravity plus 2h over t squared. Okay. If I increase gravity, or actually, you know what? What I need to do is I need to solve for t, right? Little t. That's what I need to do. Sorry. Doing some more algebra. T over m is equal to g plus 2h over t squared. T over m minus g equals 2h over t squared. We cool?
Yeah.
Is it right if I put an m up here and an m down there? I'm just trying to combine fractions here. So this is t minus gm over m. I'm going to invert both fractions, so I have t squared over 2h is equal to m over t minus gm. Now I'm going to multiply up the 2h. I'm going to take the square root of both sides. So I have t is equal to, shoot, I'm running very low on room here. I'll just do it above my head. T is equal to the square root of 2hm over tension minus gm. Okay. That's my answer. It's got weird implications, or it's got weird things happening over there. Let's see if the units actually work. Okay. What's the measurements? What is the units of the number 2?
No units.
All right. What's h?
Meters.
What's m?
Kilograms.
Good. What's t? Capital T.
Seconds.
Nope.
Oh, tension, newtons.
Newtons. Or kilogram meters per second squared.
Right.
Minus gravity, meters per second squared, times kilograms. Okay? What is a kilogram meters per second squared minus a kilogram per meters per second squared?
0.
Nope. Remember, we're looking at only the units. So this is saying like 3 blah minus 2 blah is going to equal to 1 blah. It's still going to be just kilogram meters per second squared. Are we cool with that?
Yeah.
Okay. This kilograms cancels out with that kilograms. I've got a fraction over a fraction, so I have meters over 1 times second squared over meters. Yeah?
Yeah.
Okay. Then what I have is I'm going to cancel out this meter, that meter. But remember, I'm taking the square root of the whole dang thing, because that big square root over there. So I'm left with seconds. That's pretty cool. So, the units of this answer works. Let's talk about the ideas behind it. What is this implying? Alright. If tension got really, if T were a really big number, what would happen to little t? If big T were really big, what would happen to little t? Look at this thing.
So if the tension were really big, then it would take only a short amount of time for the rope to snap?
No.
Is that no?
No. But what you're saying is, I mean, mathematically you're looking at this and you're saying if tension got really big, it's in the denominator, so the time would get smaller. That's what you conclude, right?
Right.
Now let's think about what that's telling us. That's saying if the tension, if I used a cable instead of a 755 Newton rope, but I use a cable which can hold, 7 kilonewtons or something like that, then it would take, I could pull him out of that pit in less time. That's what it's saying.
Oh, okay.
Does that make sense?
Yeah.
If I had a stronger cable, I could pull him faster. If I pull him faster, I'd be able to.
Do it in less time because you're not depending on the fact that too much acceleration would break it because
I'm less worried. Right. If I took one of the cables that's holding up the Golden Gate Bridge, I'd be less worried about breaking the cable, and I can just kind of pull really fast, assuming I don't rip his arm out of the socket.
Got it.
Okay. What about H? If H got really big, what would happen to time? Look at the equation.
It would take a little bit longer to bring them out because you have to bring them out a further space. It's a bigger distance.
Obviously, if the cliff were bigger, it would take longer. What about G? If G gets bigger, what happens to the time? This one's a little weird.
Well, I guess if G gets bigger, then the time would take, you could take him out It would take. Wouldn't it take longer to take him out though? Because if you think that he weighs more, or
All right, so now what you're doing is you're doing it backwards. You're not looking at the math, but you're saying, wait, intuitively, if gravity got bigger, he would weigh more, and if he weighs more, I would have to be more careful with this rope, and it would take longer. That's what you're saying, right?
yeah,
That's what your gut is telling you?
yeah.
Now,
But it
mathematically, we're
doesn't
looking at
really
this.
make sense with the math.
What is that?
It doesn't really make sense with the math, though, right?
No, it does. Because look, if gravity got bigger, notice that there's a negative sign over here. So you're taking some number minus a bigger number, which would make that denominator smaller altogether.
Oh, okay. So it does work. It's just you have to pay attention to the sign. Okay, that makes sense.
But it makes sense. I mean, like the math is telling us exactly what our gut is telling us. There's also a problem here. There's also a limit of something. I would say that T has to be bigger than or equal to GM. Because if T were smaller than GM, if G times M were bigger than T, then this would be T minus a bigger number. That would be a negative number, right, in the denominator? Right?
Right.
And you can't take the square root of a negative number. That's a problem. Also, if T were equal to GM, then that would mean T minus GM, which is the same, T minus T, which is 0. You would have a 0 in your denominator. There's a problem here. Right? There's a restriction of this. Why is that restriction there? What is your thoughts about that? I mean, there's a math restriction. The math restriction is there's no negatives in the square root and there's no zeros in the denominator. That's the math restriction. But what does it make sense? How does that make sense physically?
Well, hold on. It makes sense physically because it's saying the tension has to be greater than, I guess, the weight. Because if it's smaller than the weight, then it breaks automatically. Is that what it's saying?
That's exactly what it's saying. If you've got...
So, I mean,
I'm sorry?
That's where you have the maximum tension of 755, where it's saying that you can only go to that point before the rope breaks because of how much it can hold based on the weight.
No. You're going into a different direction there. But what I'm saying is, if you've got a 755 Newton rope, and Indiana Jones weighs 755 Newtons, you'll never get him out of there.
Right.
Right?
Okay, that makes sense.
Or, if you've got a 755 Newton rope, and Indiana Jones weighs 800 Newtons, you'll never get him out of there. Because
That makes sense.
it will break before he even leaves the ground. But in this case, if you look at Indiana Jones, he weighs 70 kilograms. You multiply 70 times 10, or 9.8 meters per second squared. That's about 700. So you only have 55 newtons to play with here. You're going to have to pull them out pretty slowly. That's what I'm thinking. Right? And if his weight exceeds that of the tension that the thing can hold, there's no chance. The T becomes undefined. Because if the rope's broken, it's undefined. But as far as like what is the time that you can pull him out in, you just plug in all the numbers into there and then you'd be happy. Are we cool?
Right. Yeah, definitely. Thank you.
I like that problem.
Yeah, it makes sense now.
Yeah, well, I mean, I'll be honest with you. Okay, check this out. Physics is really hard. I don't know if you figured that out.
Yeah.
Or, I don't know, is it easy to you?
No, not really. It's a challenge.
It's a fun challenge. I love it.
Yeah, once you figure it out, it's pretty cool.
But, I mean, it's not easy. So, I commend you, Julia, especially since you want to be more of an English major. This is not easy stuff, but I can tell you this. Well, I don't know if I can completely back this assertion up because I'm not very good at English. But if I can teach you to think logically, to approach things systematically, and to really creatively approach problems, I think that will make you a better journalist and a better English scholar.
Okay, so how do you think you could have increased the
Anyway, good job.
Yeah,